Hello, hi students. As part of the semester 1, we have unit 4. That chapter 2 is isomerism. We are familiar with the word isomerism. We usually see this one in organic chemistry, where iso stands for same or equal and mer stands for unit. So equal units are equal in some aspect. Here that one is usually molecular formula would be same. So the word isomers can be split into iso, which means equal, and mer is part, equal part in something. This was coined by Berzelius. So in organic chemistry, you usually find molecules with the different physical and chemical properties, but somewhere their chemical formula is same, or maybe the molecular formula is same. The molecular formula is same, but physical and chemical properties usually differ. Then for such molecules we coin the term isomerism. So even the definition also says the same, that two or more compounds with the same molecular formula but different properties makes isomers, and the phenomena is isomerism. Let us try to build a structure. A chemical formula is C3H6O, molecular formula is C3H6O. Using this molecular formula, we just try to propose two chemical formulas as structures. We just try to propose, and those two structures, from the structures you should be able to identify that the properties should be different. That properties here refers to what? Physical and chemical properties. Using this C3H6O, let us try to draw two different molecules. That's C3H6O. So three carbons are there. 1, 2, 3. And this one you just try to make an aldehyde, C double bond O and H, rest hydrogens, CH2 and CH3. Now what is this name? It becomes propanol. It becomes propanol. And you can even have another one with the same molecular formula with 3 carbons, C, C and C, with the double bond here, oxygen here. That makes us 3 hydrogens here, CH3, and 3 hydrogens over here, that is CH3. This is your ketone, which is acetone. And now you look at these two, both are having same molecular formula. The molecular formula is same. So both are having the molecular formula as 3 carbons, 6 hydrogens, 1 oxygen. That is propanol and acetone are having same molecular formula, but they are differed in their properties. So the properties here refers to what? Physical and chemical properties. Same molecular formula, different properties. Here different properties refers to different properties. What are the different properties? You can say that their chemical properties, and physical properties are different. So if physical and chemical properties are different, then you can say, so slightly I will try to adjust this. Okay, now you can see these two molecules, that is propanol and acetone, exhibit different physical and chemical properties, but their molecular formula is same, therefore they are isomers. So broadly, these isomers are classified into two categories. One is constitutional isomerism, another one is stereoisomerism. By simply changing arrangement of atoms, isomerism that arises is constitutional isomerism. This is otherwise referred as structural isomerism. Arrangement of atoms or group of atoms, if differed, then the isomerism that is arising is referred as constitutional isomerism. And the other type of isomerism you can see in the orange or maybe slightly pinkish one is that stereoisomerism. And this isomerism arises due to difference in spatial arrangement of atoms. That's stereoisomerism. And broadly, this stereoisomerism is again of two types. One is diastereoisomerism, another one is enantiomerism. And within the diastereomers, you have geometrical isomers and conformers or conformational isomers you have. Okay, we'll see that one exclusively, but let us start with the blue one that you are looking at, that is constitutional isomerism. In constitutional isomerism, the molecular formula will be same, but the arrangement of atoms or group of atoms, their attachments simply differ. That's constitutional isomerism. Definition wise, two or more molecules we consider, they have same molecular formula, but these molecules will differ in arrangement of atoms or group of atoms, and there will not be any reference to spatial arrangement, only arrangement of atoms will consider. And such phenomena is a constitutional isomerism, and the isomers are referred as constitutional isomers. Let us see one example with a C4H8 molecular formula. Using this, you just try to write two molecules with the difference in arrangement of atoms. Here you can see one is N-butane and other one is isobutane. CH3, CH2, CH2, CH3 is N-butane, and CH3, CH bonded with two different methyls. Here methyls chains are there, two chains are there, so this becomes as isobutane. That's one of the constitutional isomerism. So the various types of constitutional isomerism you come across. Different types of constitutional isomerisms are, and that is chain isomerism, another one you'll come across is positional isomerism, and functional isomerism. Metamerism and tautomerism is also there, but we will restrict to what is given in syllabus. Okay, so now let us see the first one, that is chain isomerism. This is the chain isomerism. Let us see this. So such constitutional isomers which differ in the nature of carbon chain. If the nature of carbon chain is differed, then it is referred as the chain isomerism. So under constitutional isomerism, that is structural isomerism, you see this chain isomerism. So you can say the constitutional isomerism where there is a difference in carbon chain are referred as chain isomers. And just to put up an example, I will try to make an example here. That is, we'll take pentane, whose molecular formula you can write as, here I'll write slightly. Okay, so C5H12. This I can write as 1, 2, 3, 4 and 5 carbons. Fill their hydrogens as CH3, CH2, CH2, CH2 and CH3. And another one you can write as 1, 2, 3, 4 with a carbon chain over here. That makes as CH3, CH3, CH, CH2 and CH3. Now these two are having same molecular formula, and the molecular formula is, the molecular formula is C5H12. This is the molecular formula, and this one is, how you will name this? This is N-pentane. This is N-pentane. You will write this as, here I will write N-pentane. And this is isopentane. One more also you can write as, here I will write 1, 2, 3, 4 and 5 carbons. This is CH3, CH3 and that's another CH3 over here and CH3. This is neopentane. Neopentane. This N-pentane, isopentane and neopentane are what isomers? Chain isomers. They are chain isomers. What they differ in? Carbon chain structure they differ in. So these constitutional isomers differ in carbon chain structure are referred as chain isomers. And the second type of isomerism is, under constitutional isomerism, is functional isomerism. So functional isomerism, I will take one example with C2H6O. With C2H6O, I will write here C2H6O. So two carbons, the one as OH I will write, as CH3, CH2OH. So this is your ethyl alcohol. Ethyl alcohol. And same one you can even write another form as CH3OCH3. That's your ether. That's your ether, which is dimethyl ether. Dimethyl ether. So here in this case, we just try to develop some functional group difference. We have developed the same molecular formula. We have developed a functional group difference. One is alcohol. That the first one that you are looking at here is a, what is that? So I will highlight it in a different color. Just to have a look at. That's your alcohol. This OH is alcohol, and here it is what? Ether. So what is same here? Again, molecular formula is same, but difference arises because of a functional group. Nature of functional group is differed. So therefore, you can say these are functional isomers. Such constitutional isomers having same molecular formula but difference in functional group are called as functional isomers. So many examples we can quote. We will restrict to one here. Under constitutional isomerism, the other type of isomerism you have is positional isomerism. So under constitutional or structural isomerism, we have seen chain, functional, and the third type is positional isomerism. So the name itself is suggesting that the position of functional group or certain group of atom or maybe some atom is different. So here the functional group is at a different position. Constitutional isomerism where the functional group is at a different position are positional isomers. So for example, if I have to write, see, if I will take C3H7Cl. C3H7Cl. So how many carbons are there? 3 carbons, which we will write like this with a chlorine out here. Okay, so fill the hydrogens as CH3, CH2 and CH2. This is 1 chloropropane. 1 chloropropane. Now you can simply change this position of chlorine here, make it at second carbon. Again go for filling CH3, CH and CH3. This is 2 chloropropane. 2 chloropropane. These two are what? Positional isomers. So constitutional isomers where there is a change in position of a functional group. This chlorine is the functional group here. So even you can write even with the alkene also, butene, and in that butene you can write 2 butene and 1 butene, 2 butene and 1 butene, so that they become as what? Positional isomers. So that positional isomers, in the case of butene, you can write as something, how many carbons butene is having? 4 carbons. So the same you just try to mention. You can have a double bond in the middle or at the terminal position. So here it becomes as CH2, CH and CH2 and CH3. This is 1 butene, and here overfilling hydrogen CH3, CH, CH and CH3. So this becomes as 2 butene, 1 butene and 2 butene. The difference is in position. Here 1 and 2 are indicating the position of a double bond. So they become as what? Positional isomers. So these are the constitutional isomers. So the second part of that isomerism is, we have seen the constitutional isomers here, and the second part is your stereoisomers. This is the second part that you can see in stereoisomers. So what are these stereoisomers? Let us see that. Stereo is indicating space. The word stereo means what? Space. So whatever the word that you are looking at, stereo, the stereo word is what? Space. Spatial isomers, you can say. Spatial isomers. So such isomers that differ in spatial arrangement of atoms, not simply connectivity. There is no change in connectivity. Connectivity will remain same, but spatial orientation of atoms simply differed. Then such kind of isomers are called spatial isomers or stereoisomers, and these stereoisomers are of two types. One is enantiomers, other one is diastereomers. Enantiomers and diastereomers. So enantiomers are molecules which are non-superimposable mirror images having similar connectivity. The connectivity will remain same, but the spatial arrangement of atoms simply differs. So have a look at this enantiomers. So in this case, substituted methane have taken with 4 different groups or 4 different attachments here: bromine, chlorine, fluorine and hydrogen. And its mirror image, it's a mirror image. And the blue one that you are looking at is the mirror. So if I mirror this one, bromine will fall this side, chlorine will fall this side, but fluorine will fall this side, and hydrogen. So these two are mirror images, and now you try to superimpose this onto this one. bring this image onto this one. That's it. So what happens? They are not superimposable. They are not superimposable, and mirror image relationship is there. Then they are referred as enantiomers. They are referred as. And similarly, the another one you are having is diastereomers. Such stereoisomers where there is no mirror image relationship, this should not be there. But earlier case we have what mirror image relationship is there, but now in this case you don't have a mirror image relationship. So what you can say, they are not mirror images of each other, and they are non superimposable. The molecules will have the same connectivity. Okay, so here in this case, look at tartaric acid. Three molecules of tartaric acid I have shown you. So as you have already seen RS nomenclature in your previous classes. So if I have to say, look at the first molecule and second one. 1 and 2 you have look at, these two are what? Mirror images. So as these two are mirror images, they are not diastereomers. 1 and 2, look at, they are exactly the mirror images. Oh, here I have dot line is indicating mirror. So these two are mirror images. These two are mirror images. What you can say? Mirror images and non-superimposable. So 1 and 2 will become as what? Enantiomers. 1 and 2 will become as what? Enantiomers. Look at the molecule 2 and 3. Molecule 2 and 3. They are not mirror images and non-superimposable. So 2 and 3 will become diastereomers. Now find the relation between 1 and 3. Even 1 and 3 also are not mirror images and they are non-superimposable. They become diastereomers. Here you have taken two stereocenters. Okay, this is two stereocenter molecule, and that's in the case of tartaric acid. You come across diastereomers like that. So 1 and 2 are enantiomers. 2 and 3 are diastereomers. 1 and 3 are diastereomer relationship they have. So these are having same molecular formula. Their difference is in spatial arrangement of atoms. So as such, you can say they are stereomers, and within stereomers, 1 and 2 will become enantiomers. Here 2 and 3 will become diastereomers. 1 and 3 also will become diastereomers.